conjecture with descendants, please.
Oh, yeah, first of all, I wish to thank the organizers for the invitation. It is my great pleasure and honor to have the opportunity to give a talk in this online M seminar. The title of my talk today is Remodeling Conjecture with Descendants. This is based on joint work with Bohan Fang, Song Yu, and Zhengyu Zong. They are all based in Beijing, and yeah, so the preprint is on archive. Oh, um, oh, the remodeling conjecture proposed by Bouchard-Klemm. Sorry. The remodeling conjecture proposed by Bouchard-Klemm-Mariño-Pasquetti in 2007 to 8 is so 2007 to 8 is a version of all-genus mirror symmetry for toric Calabi-Yau threefolds. So in this talk, a Calabi-Yau threefold is a Kähler manifold, or more generally orbifold of complex dimension 3, such that the omega 3x is trivial. So in general,
So it doesn't have to be toric today, so it can be compact.
right? So yeah. So I will right, but so yeah. So just for the first few slides, there will be some general statement, but for what I can prove, it will be toric. Yes. So sorry. So the remark. Oh, I apologize. So yeah. When I say yeah, in this talk, Calabi-Yau threefold is a Kähler. So when it's toric, I will say it's toric. Yeah. Thanks. So yeah. So let me just recall some like general principle for mirror symmetry. So in general, mirror symmetry relates a model on a Calabi-Yau threefold X defined curly X defined in terms of the symplectic structure on X to the B model on another Calabi-Yau threefold X check the mirror of X, defined in terms of the complex structure on the mirror. So there are many versions of mirror symmetry. One version is homological or categorical mirror symmetry proposed by Concevic in 94. So it is equivalence to of the category of A branes, category of Fukaya category of Lagrangian submanifolds, and the category of B branes, the derived category of coherent sheaf in the mirror. So there are many mathematical aspects of mirror symmetry. I personally am most interested in enumerative geometry. So for me, such as Gromov-Witten invariants, which can be viewed as a mathematical theory of A-model topological strings on a Kähler manifold. So for this aspect, so A-model topological strings on this Calabi-Yau threefold should be mirrored to the mid-model topological strings on the mirror Calabi-Yau threefold. And so the topological strings, so they will depend on like Kähler parameters on X or classified Kähler parameters. So say there are P Kähler parameters. So there should be some neural map relate the Kähler parameters on the A side to the complex parameters, local coordinates on the complex moduli on the B side. And the A variation Hodge structure, Dubrovin connection is defined in terms of genus G Gromov-Witten invariants counting holomorphic spheres. whereas on the B side, the variation of Hodge structure is just the classical Gauss-Manin connection given by period integrals on 3 cycles. So A model, so this FG, the A model topological, genus G A model topological string partition functions are just mathematically defined as genus G Gromov-Witten potential. It's a generating function of genus G Gromov-Witten invariants. So for B model side, in genus-zero, they are just classical period integrals. But for higher genus, there's a physics theory, but I think for like mathematical definition is much more difficult for a higher genus. So it says said Gromov-Witten theory on the A model side. Gromov-Witten theory, which can be viewed as a mathematical theory of A model topological strings, are defined for smooth projective varieties, not necessarily Calabi-Yau or dimension 3. These are defined back in the 90s. And like a generalization, sorry for the typo in the, it's a Deligne-Mumford stack. There's some typo, Deligne-Mumford stack. So for the orbifold case, it is also defined by early 2000, by 2000. So the A model topological strings, which are rigorously defined as Gromov-Witten theory, now is defined for all genus for projective varieties, or more generally compact orbifold whose coarse moduli are projective varieties. But higher genus B model, I think now, Lino is an expert on this. So now categorical enumerative invariants provide a mathematical definition of all genus B model topological string for a proper non-singular Calabi-Yau varieties. Today, these are, the higher genus mirror symmetry is, still very difficult. But I will consider the toric case, which is much better understood. A Calabi-Yau threefold is toric if it contains the three-dimensional complex algebraic torus as a dense open subset, and the T echelon itself extends to X. So for example, the total space of O minus 1 plus O minus over P1, also known as the resolved conifold or local P2, the total space of O minus 1 over P2. And toric Calabi-Yau threefolds are never compact. So our results will include both toric Calabi-Yau smooth toric Calabi-Yau threefold and also toric Calabi-Yau three orbifold, and they should be symplectic. They should come from GIT quotients. So for simplicity, in most of the talk, we will just assume the X is smooth. So in this toric case, so the A model is a symplectic toric Calabi-Yau threefold. So it's a GIT quotient of some complex vector space by the linear action of a torus G. And so as a complex manifold or orbifold, and so as a symplectic manifold or orbifold, there's we consider, so this G action restrict to Hamiltonian action by the compact torus GC of dimension P, and so we consider the symplectic reduction. with respect to the standard symplectic form on CP plus 3. So now this P, which is the dimension of the so when GC acts freely on the preimage of a regular value of the moment map of the compact torus, so we get a smooth toric Calabi-Yau threefold together with a symplectic structure, and yeah, so the parameterized the scalar parameters correspond to a choice of a point in the dual of the Lie algebra of the compact torus, which is, say, p-dimensional. And so to match the B side, there's a complexified scalar parameter. So now tau 1 to tau p are complex numbers. And let G hat be the number of compact divisor and N hat be the number of non-compact T divisors. For example, in local P2, there's only one compact T divisor, which is the 0 section, and there are 3 non-compact T divisors. So G hat is 1 and N hat is 3 for local P2. And then like the yeah, so then the for toric Calabi-Yau threefold is non-compact. So the 6 yeah, so these are the cohomology in terms of G hat and N hat. So on the mirror side, so it's given by so-called Hori-Vafa mirror. So given the toric data, yeah, so one can write down this explicit Hori-Vafa mirror of this form. So it's a hypersurface in C2 cross C star 2, where little u and little v are coordinates on the C2, and big X and big Y are coordinates on C star. And so it's a family of hypersurface. So it's the mirror family is also a family of Calabi-Yau, non-compact Calabi-Yau threefold parameterized by P complex parameters. And there's indeed an explicit mirror map relating the tau, the complexified scalar parameter on the left-hand side and the complex parameter on the right-hand side. And the holomorphics, so yeah, yes.
So the X is a symplectic toric Calabi-Yau threefold. So that's where P plus 3. So what does the P appear?
Oh yeah, it's because G is like p-dimensional torus. So
I see. So you have a much larger group, could have a much larger group acting.
Yeah. So right. So it's like in this quotient will have like the second Betti number will be equal to p.
Okay. So that the second Betti number of this of X, right?
Yes, thank you. So it will be equal to p, and also this p, because it's like the dimension of the second cohomology. So this p is also the dimension of the scalar moduli.
I see. Okay.
Yeah, and then the mirror will also have like p parameters. It can be explicitly written down, and the mirror has p parameters little q1 to little qp. And then for a non-compact Calabi-Yau threefold, there are many holomorphic three forms. So it's actually this very explicit. We just take the standard holomorphic form on C2 cross C star 2 and take the residue along this hypersurface. And then this mirror family, we can project it to C star 2, and it's a conic bundle such that the vibration degenerate along the mirror curve, which mirror curve is this just defined by this. This is a Laurent polynomial in X and Y with coefficients in in little q. So this is mirror curve. So so it will be a genus G hat and have puncture Riemann surface where G hat is equal to the dimension of the first cohomology of X, and N hat is okay. So it's related to the topology of the original toric Calabi-Yau threefold. Sorry, I think so that's just the basic geometry. So I state the original remodeling conjecture, and then in the purpose of the talk today is to describe a general extension of this conjecture. So in this case, so on the A side, we can define Gromov-Witten invariance. It's non-compact, but we can define it using, so we can define it using torus localization. So we can consider Gromov-Witten invariance, counting genus G holomorphic curves in X, and Fg comma N is open Gromov-Witten invariance, counting holomorphic like border Riemann surface with G handles and N holes. Within a Lagrangian, which is called the Hori-Vafa A brane. So this invariance also depends on some framing. So because of non-compactness, it's defined and computed by torus localization. So there's Tx on the canonical line bundle on the toric Calabi-Yau threefold. But since the canonical line bundle is trivial, so this gives us this action gives us a character whose kernel is so-called the Calabi-Yau torus. So two-dimensional Calabi-Yau torus acts trivially on the canonical line bundle, and we call it Calabi-Yau torus, and we call it maxima compact subgroup, which is a compact two torus. We call it compact Calabi-Yau torus. So the nice thing about this Hori-Vafa A brane is actually the compact Calabi-Yau torus acts on L. So therefore, it will act on the moduli of holomorphic curves on curly X with boundary in L. So that's why we can use this two-dimensional torus to define and compute this Gromov-Witten and open Gromov-Witten invariance. So in general, open Gromov-Witten invariants are like, especially in like higher genus, is difficult to define. But in this case, we can define it in this way, and it can be computed. In terms of like Hodge integrals, which are intersection numbers on moduli space of curves, stable curves. So on the B model side, so you see if we follow the B model side, we have this very explicit holomorphic three form. We can integrate it on like integral three cycles on this. Sorry, this should be X check, and it will gives us the genus G B model genus G topological string partition function. And so I don't know, maybe Lino knows how to define the higher genus B model for such a non-compact Calabi-Yau threefold using the like categorical innovative invariance. Maybe that's some work in progress.
And can you, so you have the spectral curve which depends on the parameter Q. Can you just quantize it and look for solution to the quantum differential equation with some normalization condition? Will it be the full part?
Right. So right. So like I think Kontsevich and Soiberman has this generalization of this topological recursion, right? So today I'm just doing this very classical. So the classical is just this mirror curve, and with omega 0, 1 is y dx. Y is x is minus log big X, and y is minus log y, and x hat depend on f. Like the left-hand side, in the open string sector, it depends on this framing f. So the right-hand side, in the definition, so it should also depend on little f. Yes.
I forgot, f is what? Is a number, or you multiply y?
F right now. So on the left-hand side, actually, this framing is so the left-hand side. This actually there's some So left-hand side, this framing under large M duality will be related to the framing of knots. Yes. So the open Gromov-Witten invariants depend on the framing. So the right-hand side, you see that the omega 0, 1, right? So we have dx hat. So dx hat will be dx plus f dy. So we change omega 0, 1, so in this way. So then this will change the invariant. That's the F dependence on the right-hand side. So there's also omega 0. So I will say more about how this is defined. So but with this omega 0, 1 and omega 0, 2, so there's this Chekhov-Eynard-Orantin topological recursion, which is defined like very classical, and like classically and rigorously, and just use like so this we have this mathematically defined higher genus B model, including the open string sector, thanks to this topological recursion invariance on the mirror curve. So the remodeling conjecture is saying that it's a precise relationship between the between the omega gn on the B side and the open Gromov-Witten invariance FGN, and also so omega gn is defined recursively from omega 0, 1 and omega 0, 2, and omega g0 is can be defined in terms of omega g1 and bound to the G close Gromov-Witten invariance. Yeah, surprisingly, like the close Gromov-Witten invariance will actually not depend on the equivariant parameter if we use the Calabi-Yau 2 torus. If we use the 3 torus, it will depend, in general, depend on the equivariant parameter. The remodeling conjecture when X is smooth, and then they also have the conjecture for toric.
Sorry, Melissa, I kind of lost track. So on the B side, does the n have any geometric meaning, or is just something that shows up in this recursion?
So can you ask again?
So I was asking, on the B side, the n, does it have a geometric meaning, or is it just you get it from this recursion?
Oh, you mean the n?
Yes. So on the left-hand side, the n is the number of boundary components, right?
Yeah, so the right-hand side, there's also, so I think, so later I will actually give a more precise definition of omega gn.
Okay, thank you.
Yes. So Bohan Fang and Zong and myself a few years ago, we proved the orbifold case in full generality. So this talk is, so we want to formulate and prove a remodeling conjecture for remodeling conjecture with descendants. So this can be viewed as a all-genus T prime equivariant descendant mirror symmetry. So, so then I first need to clarify like what are the, so on the A model side, they will be all-genus T prime equivariant Gromov-Witten invariants on the toric Calabi-Yau threefold. So let me give you the precise generating functions. So this, okay, so this page, so we consider the moduli space M bar G and X beta of genus G M pointed degree beta stable maps to the toric Calabi-Yau threefold. So it is in general singular Deligne-Mumford stack with a perfect obstruction theory of dimension n, where n is the number of mark point. So now we want to, so this moduli space are in general non-compact because our curly X is non-compact. But we still have, but it still has the perfect obstruction theory or virtual bundle, tangent bundle of dimension n, where n is equal to the number of mark points. So let EVI be the evaluation at the ith mark point, and let Li be the line bundle on this moduli space whose fiber over a moduli point is just cotangent line at the ith mark point. So now the T action, so the three-dimensional torus acts on X, and it induces a torus action on the moduli space of stable maps. And the evaluation map is T equivariant. And also this line bundles we just described, we can also equip it with a T equivariant structure. So the reason we want to oh, so maybe let me see like why so in the descendant version, so because it's a toric threefold, so any toric threefold, not necessarily Calabi-Yau, there's a Landau-Ginzburg mirror. Yeah, and also it's an equivariant Landau-Ginzburg mirror, which is three-dimensional. So then we can consider the equivariant with respect to the three-dimensional torus. But if we want to reduce to a theory on the mirror curve, so so we can only use the two-dimensional Calabi-Yau torus. So that's why in the rest of my talk we will restrict to this Calabi-Yau torus. So it's so basically if we take some T prime equivariant cohomology, so now with complex coefficient, it turns out that in this very nice case, we don't need to work over Novikov ring, and the complex mirror is actually defined over the complex field. And so given gamma 1 to gamma n, which are cohomology, T prime equivariant cohomology classes on X with complex coefficient, and A1 to AN, which are non-negative integers. So we define T prime equivariant descendant Gromov-Witten invariant of X by the right-hand side. So so because the moduli space M bar G and X beta is not necessarily compact, so we cannot we don't have a non-equivariant definition. So what we do is we just use the localization formula to define this invariance. And so the right-hand side is defined because if we consider the T prime fixed locus and it is always T prime fixed substack. It is always proper or compact. So the right-hand side can be defined. So the virtual normal bundle, so there's a virtual tangent bundle on the whole moduli space. And along the fixed loci, we can decompose it into the sum of like the torus fixed point and torus moving part. And torus fixed part defines a virtual tangent bundle on the T prime fixed substack. And the moving part defines the virtual T prime equivariant virtual normal bundle. So so now we want to, let's see. Okay, so now we have this. So we want to, so this is some correlator, G M-pointed correlator and fixed degree beta. And next we want to define some correlators. We want to sum over the degree, and we also want to add like all possible insertions. So this correlation function will depend on, so BQ beta is like novical variable, and also tau will be a complexified Kähler parameter. It is just some point, tau is just a point in the second cohomology with complex coefficient. And because we want to define equivariantly, we will choose a T prime equivariant lift of tau. And so in particular, when all the AIs are 0, so we take this correlator is just T prime equivariant primary Gromov-Witten invariance. And in particular, when there's no mark point, we don't need to insert anything. Let's say when G is greater or equal to 2, the stable case. So this is the closed Gromov-Witten invariance in the original remodeling conjecture. So this equivariant descendant Gromov-Witten invariance can be viewed as like generalization of this. And so so today the remodeling conjecture with descendant will involve like all-genus T prime equivariant descendant Gromov-Witten invariance that we just defined. So, but before doing so, I would like to describe the genus-zero version. So, so the genus-zero version can be viewed as a Hodge-theoretic T prime equivariant mirror symmetry with integral structures. In general, the integral structure in a variation of Hodge structures defined by genus-zero Gromov-Witten invariance is given by category of B branes, coherent sheaves. And the B variation of Hodge structure is given, the integral structure in B variation of Hodge structure is given by category of A branes, Lagrangian submanifolds. They represent integral 3 cycles. Okay, so let's let's fix some notation. So let T prime CP the compact 2 torus, and let M prime and M prime denote the character and co-character of the Calabi-Yau torus. So if we tensor by R, so they can be identified with the dual of Lie algebra of the compact Calabi-Yau 2 torus and the Lie algebra of the compact Calabi-Yau torus. So now, so we want to introduce some geometry. So without going to details of the combinatorics of toric geometry, so let me first describe something which is for like general toric variety, not necessarily Calabi-Yau or three-dimensional. So it's defined by a fan, and each cone in a fan corresponds to a T-orbit closure V sigma. So if cone is d-dimensional, then V sigma is codimension D. So the core of X is the union of compact T-orbit closures. So for example, if curly X is local P, if X is local P2, then this core is just a zero section P2. Given given some primitive and generic co-character of the Calabi-Yau torus, so this gives us one parameter subgroup in the Calabi-Yau torus, and it restricts to a Hamiltonian U1 action. So let mu v be the moment map of this Hamiltonian U1 action. So it's a real value function on the Calabi-Yau 3, toric Calabi-Yau 3 for X. So now fix such a choice, and we define X plus minus to be the union of V sigma, to be the union of T-orbit closure on which this real value function is bounded below. So X plus is bounded below, X minus bounded above. So so of course the core is contained in the both X plus and X minus. So in general, it's contained in the intersection. But we want to choose generic, if we choose if we choose the V, the one parameter subgroup generically, then their intersection is exactly the core. So we know that for compact Calabi-Yau threefold, the category of B-brane, we should take the bounded derived category of coherent sheaf on X. But it turns out in this for this non-compact case, more specifically for toric Calabi-Yau threefold, there are several interesting category of B-branes. So I have this diamond. So the diamond is like we can consider, so the coherent sheaves on X, since it's a smooth toric Calabi-Yau threefold, or more generally smooth toric Calabi-Yau 3 orbifold. So we can, it's equivalent to some perfect complex of vector bundles. And so we can consider the subcategory such that the cohomological sheaves of such a complex is supported on X plus or X minus, or just compact support. So we can call it like bounded coherent sheaves with bounded below support, bounded above support, or compact support. And then we can consider their Grothendieck groups. So for the usual like derived category, it's the Grothendieck group is a ring, and it's generated by line bundles additively. And for the other three derived category of B-branes, they are KX modules, and it's generated by structure sheaves of V sigma, where V sigma is like bounded below or bounded above, or just compact. And we can also consider, so yeah, the T prime equivariant versions. And we have T prime equivariant case. There's T prime, K prime, the T prime equivariant K series. And if we do the T prime equivariant version, then this morphism, natural morphisms are actually injective. So for non-equivariant, this is, yeah, the map from the compact supported K series to the K series is not injective, but but equivariant version, this is injective. And if we tensor by the fractional field of the two equivariant parameters of the compact of the Calabi-Yau two torus, then they become isomorphisms. So now, following Iritani, we want to define K-theoretic framing. So we just need to define it for like the usual T prime equivariant K series, and then we can restrict this definition to the bounded below, bounded above, and compactly supported T prime equivariant K series. Yeah, so given some curly E, so it's like an element in it's a T prime equivariant K series class. So yeah, so we can just consider T prime equivariant vector bundle, and this is some characteristic class. So the gamma T prime is some characteristic class of the tangent bundle, and there also this twisted equivariant chain character. So the gamma class is multiplicative and the chain character is additive. So I only need to provide a definition for T prime equivariant line bundles, and it's given by the formula of the last line. So this gamma is like a degree 2 cohomology class. Z should also be viewed as a degree 2 cohomology class. So this twisted chain character has degree 0. And this twisted, like this gamma class, has like degree equal to the rank of the vector bundle. So now we have this so if we given some T prime equivariant K series class, we define it's similar to what like Iritani did. So T prime equivariant quantum cohomology central charge is just, so this is a mod, it's a genus-zero 1-point descendant equivariant Gromov-Witten invariance defined this way. So now we want to have, so T prime equivariant mirror. So we have a mirror curve, which is just a hypersurface in C star 2. So the T prime equivariant mirror is we just take the universal cover C2 of C star 2 and consider C tilde Q, which is the like pre-image of the mirror curve in C star 2. So now we want to so we have, so this U1 U2 will have so this U1 U2 will correspond to the equivariant parameters on the yeah, I don't know if I should call it A side because you see this quantum cohomology central charge. Yeah, so it's defined in terms of a model topological string like genus-zero Gromov-Witten invariant. but we are like the boundary condition is a B-type boundary condition. It's a coherent sheaf. So now on the other side, but we consider the B side is the mirror curve side. So the mirror curve, so we will just consider like Lagrangian, but on the mirror curve, any curve is Lagrangian. So this is our descendant mirror theorem. So for any T prime equivariant sheaf with bounded support, bounded below support, so we have we will send it to some relative one cycle on the equivariant mirror curve C tilde Q. And this X hat is, defined depend on U1 and U2. And we relative to like the real part of X is like plus infinity. And then, so there's a homomorphism. There's a unique homomorphism such that the T prime equivariant central charge of this of this K-series class is equal to the like this oscillatory integral of the mirror cycle, one cycle. So the left-hand side depend on tau, and left-hand side depend on the complex parameter Q, and they are related by the mirror map, which is explicit. So it's not hard to show that if we it's not hard to show that if tensor by Q, this is an isomorphism. But actually, so that's what we could we knew last year in 2024. But early this year, we finally like this mirror map between so mapping a bounded below coherent sheaf to a relative one cycle on the T prime equivariant mirror curve. So it's actually, so it's an M prime equivariant, and it's actually an isomorphism. So we match the integral structure. And also you see like the choice of V, there's a wall and chamber structure. So so I just so this is the local P2 case. So for example, so the bounded below like sheaf, it depends on choice of V, as we can see. So and then the left-hand side illustrate the image of X plus under the moment map. And the right-hand side correspond to like the infinity defined by this real part of X hat. So for example, just let me take this one chamber. So it's a very explicit. So for example, if we take the structure sheaf of this, zero section P2, then the mirror cycle is just this oval. Can you see my cursor? Oh, okay.
Yes, we can see the cursor moving.
Yeah, right. So then if we consider structure sheaf of this non-compact, so this is just an affine line. And then, so the mirror cycle will have like it will be non-compact, but the infinity will approach this puncture. So that's, so that's the correspondence. And actually using this, we actually, there's a Hosono conjecture, which is like, I think more than 20 years. So if we consider the central, so if we take some compactly supported case theory, so then we can define non-equivariant central charge. So this expression a priori depends on Z, but actually it does not depend on Z, and also by a string and dilaton equation. This is actually a generating function of primary Gromov-Witten invariant of the Calabi-Yau toric Calabi-Yau threefold. And then the Hosono conjecture says, again, there's a isomorphism, we match the lattice, the compactly supported K-series of the toric Calabi-Yau threefold. There's a mirror map, which is the isomorphism to the, integral, like third homology of the mirror. And this quantum cohomology central charge is equal to like this integral, period integral of the holomorphic three form under the mirror map. Oh, so maybe I'll just say, so now, like in the remaining, so this is the genus-zero. Yeah, so this is this is a genus-zero descent. So then the remaining of this talk, so we will describe a higher genus version of the central charge, and the right-hand side will be a higher genus version of oscillatory integral, where we replace the y hat dx by omega gn. So let me briefly describe the definition of like this class, the original version of Eynard-Orantin topological recursion. So we have this y, which is log big Y, and axis, which is, so recall that we have this mirror curve in C star 2, and big X and big Y are just the coordinate on C star 2, and little x and little y are coordinate on the universal cover C. So the initial data, like we should think omega 0, 1 is correspond to like disk invariance. So it's y, just y dx. And omega 0, 2 is so-called Bergman kernel. So this is a meromorphic symmetric form on the compactified mirror curve, characterized by the following properties. So it has a double pole along the diagonal, and it's holomorphic away from the diagonal. So the local normalization is near, in the local holomorphic coordinate, like it's 1 over z1 minus z2 squared. So the normalization is like 1 over z1 minus z2 squared plus some holomorphic and symmetric function h z1 z2. And but after that, there's also like when the genus of compactified mirror curve is greater than 1, there are a holomorphic 1 form. So we also need some global normalization to uniquely fix this B, omega 0, 2. So it's given by choosing a symplectic basis. So for the purpose of Gromov-Witten, like to mirror symmetry involving Gromov-Witten invariance on the A model side. So so this symplectic basis is just a basis of the complex first homology, not necessarily integral. So this is a normalization. This will be uniquely characterized. So this is a definition of omega 0, 1 and omega 0, 2. And actually, we know how to normalize it such that the resulting invariance will be the Gromov-Witten invariance on the A side. And so so let me just say, so this will define we can use this data to define the recursion kernel. And so omega 0, 1 and omega 0, 2 is like the unstable case, is initial data. And when 2g minus 2 plus n is greater than 0 and n is greater than 0, so it can be defined recursively. So maybe, without describing it in great details, let's just say that omega 2g minus 2 plus n is some symmetric, meromorphic symmetric M form on the mirror curve, on the compactified mirror curve, which is holomorphic away the critical point. And the residue is 0, so it's like differential of the second type. And the omega g0 can be obtained by omega g1. So now the thing is now we have already defined this. So this is a higher genus version of the central charge, quantum cohomology central charge. So now we take n element is this bounded below equivariant K series. And then we define this genus G n-pointed descendant. It depends on this formal parameter Z1 to Zn, and also depend on equivariant parameters. In particular, when so Gn is 0, 1, and this is just the quantum cohomology central charge. So on the other hand, so now if we give gamma 1 to gamma n, which are this relative one cycles. So we define, so instead, so we define this oscillatory integral along this gamma 1 to gamma n. So we take omega gn and define this oscillatory integral.
Sorry, I forgot the notation. Your omega gn, it's same as Einar and other people, or it's something which you defined in the integral. I
so the
forgot.
omegas, so this is defined because this relative cycle. So gamma 1 to gamma.
No. Just about the notation. Omega gn on this parameter. What is omega gn? It's
This omega gn is the so let me so I have some. So this omega gn is this omega gn.
It's same as Eynard-Orantin, yes.
Yeah, so yeah, it's the
Okay.
Eynard-Orantin. Yeah, great.
Yeah,
so
you use them with certain, okay.
So we take this omega gn and right, so this x hat, right? This s hat is the x hat. We have this. So basically, you see this. So this is like the higher. Yeah. So like this is the higher loop version of this integral of like oscillatory integral y hat dx. Because this y hat dx hat is omega 0, 1. So yeah, so then what, this is the higher loop version. So we have this all-genus descendant mirror theorem. Sorry, I think yeah, yeah, right. So it's the same. So we have this mirror map which send like this bounded below element in the bounded below equivariant K series on X to this relative one cycle. So yeah, so this is like match the integral structure, and we have this equality. So this is our result of all genus descendant mirror theorem. Yes, I think so. Can I have like maybe 1 minute to describe the
Sure,
idea?
go.
Yes, so yes. So the idea is on A model. So it's like, yeah, so it's equivariant toric. So the all-genus descendant, there's some given tau formula of equivariant Gromov-Witten theory, and there's also the orbital version. And so using that, and we can derive this some graph sum formula. So there will be so the quantization formula can be written as a sum over stable graphs. And also omega gn, so we know like it is uniquely determined by this topological recursion, and this unique solution has a formula in terms of sum over stable graphs. And then it's sum over the same graph. It's just the weight are in terms of the B model invariants. And so we take this graph sum formula for omega gn and we integrate. So notice that the vertex edge and like dilaton leaf contribution only depends on the closed string parameter little q. And all the like one form part, the form part is all the dependent on the the point P1, Pn is like via this n like leaves. So when we do the integral in our statement, we only need to integrate the leaf terms. So we get this expression for the graph sum format of our like higher loop version of the oscillatory integral. And so now we just need to match the contribution of each graph. So for the vertex, edge, and leaf term, so we, in our previous paper, the original proof of the proof of the original remodeling conjecture, we use the genus-zero mirror theorem to match the vertex, edge, and leaf term under the mirror map. So now we just stated this Hodge-theoretic T prime equivariant mirror symmetry with integral structure, which is genus-zero equivariant descendant mirror theorem. So then now use this, we can match the leaf terms under the mirror map, relating Kähler parameter on the A side and complex parameter on the B side, and also the gamma J, the A cycle on the B side, and the B cycle on the A side. Okay, so yeah, thank you very much. Yeah.
Okay, thank you. So questions? I see a lot of applause from the audience. Now, are there any questions?
Oh, there's no.
So the only way to define this omega gn is through this recursion. There is no other geometric interpretation or something like that.
It depends what you call geometry. So at least, I don't know, in that paper with Maximevich, Melissa mentioned, we interpreted it in terms of quantization of certain Lagrangian subvariety. But it's a different it's not a geometry of moduli spaces, of curves or something like that. It's kind of external geometry, just to understand the formulas.
So it has nothing to do with this kind of toric variety. It's more like a general.
Yeah, it's general. But I don't know. I mean, it's not a question to me. It's a question to you, Melissa. So I don't know. I mean, it's... So I do not know whether there is a kind of direct geometric way to understand this omega gn. Okay, so I don't know. Maybe more questions or comments or whatever.
Yeah, thank you for your attention. Thank you for coming.
Yeah, thanks for coming and giving talk. I mean, it's interesting. I mean, this Eynard-Orantin machinery, it's kind of, you know, like you put something in it, you press the button and it spits this omega gn. So then, so it's still a bit mysterious, yeah, what's going on. And you can do it for toric threefold, threefolds and orbifolds with descendants, yeah?
Yes.
Okay. Yep, and this machinery, it does not work for non-toric, like for compact, of course, it does, as far as I know. But there are some alternatives what to do with Gromov-Witten invariants for compact Calabi-Yaus when you do not have the torus action. Actually, I think we'll have a seminar talk of Sergei Alexandrov. He's a physicist. They have some ideas which looks a bit crazy to me, but yeah. So it's strange. If I remember correctly, they somehow write as a building block, they used not this spectral curve because there is no spectral curve, but they use Gromov-Witten invariants for the resolved conifold, which you can do using, I mean, it's non-compact, but it's a building block, but then they do something with it and spit out Gromov-Witten invariants of compact Calabi-Yau threefold. So
that's really interesting.
Yeah, it's very strange. Yeah, but interesting, but strange. Okay, more questions? Well, if there are no more questions, Melissa, thank you very much for your talk.
Thank you.
Thank you, and this is it for today.
Yeah,